Okay, yeah, so here is our second video. We're going to talk about Bayesian updating, or if you have learned about that, it's just nothing but the Bayes theorem. Okay, so first let me tell you something that you need to know before the main topic. We need to remind you about the law of total probability, which is nothing but a probability theorem. So this will be a component of the Bayes theorem. So what's that? The law of total probability is the following. Suppose I have a set of events, y1, y2, and yk, okay, up to yk. So events are the collection of some possible realizations of your random variable. For example, if you are rolling a dice, then one possible event is for you to see odd numbers. Then the probability for that event, odd numbers, is just 1/2. Anyway, if you have a set of events that are mutually exclusive and completely exhaustive, that means this means they do not overlap, and this means the probability for all of them is 1. And x is another event. Then we have the following. If I want to calculate the probability for x, then I can divide this probability into several parts, and each part is the original probability times the conditional probability. It's the probability for event y to occur, and then times the probability, the conditional probability given that y has occurred. What's the probability for x to occur? So from if we want to explain with figures, the circle here means x, and those three different areas means y1, y2, and y3. This theorem is nothing but saying the probability for x is the sum of these three pies, okay? And each pi can be calculated in this way. I know what's the probability for y1 to occur. And I know, given that y1 has occurred, what's the probability for x to occur. So the product of these two will be nothing but this pi. And what I want to do in law of total probability is to sum them up. Okay? Yeah. So let me assume we all know what's that. Okay. So let's start our discussion about belief updating. This is the case. There is something that we do not know. For example, something that is random to us. So we only have a belief on it. We do not know what's the exact number. There is some unknowns, and for them, we have original estimates. We have something we call the prior belief or prior probability for the occurrence of an event. For example, if I give you a coin, it's possible that your prior belief for getting ahead is 1/2. So you assign different probabilities to different possible realizations. If I give you a dice, then your prior probability will consist of 6 numbers. You need to assign probabilities to the 6 possible outcomes. Okay? When I give you a coin, you form probability by assigning 2 numbers, and certainly the sum of them will be 1. So for example, you believe that the probability for getting ahead is 1/2. Okay? Your prior belief before you do any experiments. If this estimation or this belief is correct or accurate, the relative frequency of this event should be close to my prior belief. What does that mean? Suppose I really toss the coin flip the coin for about 100 times. Then one possibility is for me to see 48 heads, right? If I really see 48 heads, then I am somehow confirming this prior belief because this relative frequency is very close to 1/2. However, if I see 60 coins, if I see 60 heads, then that's another story, right? I somehow would guess that this coin is not 100% fair. If when I when I flip this for 100 times, but I see 90 heads, then I have a very strong belief that this head and this coin is not fair. Okay, because if the coin is really fair, the probability for me to see 90 heads out of 100 draws will be very small. Yeah, and that's why I would update my belief. Okay, when I see this, when I see a particular observation, when I see an experiment outcome, I would update my belief according to my observation. So we expect observations to follow our prior belief. Otherwise, we would update our belief to a posterior belief. Bayes' theory is telling us how to do that. So let me use the following example. Suppose we have a product to sell. We do not really know how consumers like it. So let's assume there are two possibilities. Either our product is popular or unpopular. So let's assume that I have a prior belief on the product is popular, that is 70%. With a 70% confidence, I believe the product is popular. So I am somewhat confident with my own product. So I guess it's not so ugly. I guess it's somewhat popular. So now it's time to do the experiments. I open my store, I put my products there, and then consumers come and leave. Suppose one consumer comes, then she may buy this product or go away, right? There are two possibilities. Suppose I know if the product is popular, then the buying probability is 60%. But if the product is actually unpopular, then the buying probability is 20%. So here, I need to assume these two numbers are given and fixed. I somehow just know it. Okay? I know these two probabilities. The only thing I do not know is whether my product is popular, whether my product is the good product. Okay? So suppose this event G occurs once. That means one consumer comes and goes away. I want to know what should be my updated belief on what's happening here. What's my posterior belief on the popularity of my product? So it's time to do calculations. We're providing a table here. So in this joint probability table, here I have two known probabilities. These are my prior belief about whether the product is popular or unpopular. These two numbers are my prior beliefs because they are at the margin. They are called marginal probabilities. So we also have those conditional probabilities, right? I know if the product is popular, then the probability for one to buy it would be 60%. This will be 1 minus the probability for the consumer not buying it. Or we should say that if the product is popular with only 40%, the consumer will not buy it. But if the product is unpopular, then the here this should be go away. So this should be G. Go away. Okay. On the other hand, the probability for the product to not be bought when it is unpopular is only 20%. Okay? What am I talking about? Anyway, let me say that again. If the product is unpopular, the probability for the person to buy it would be just 20%. These are something I know. So according to that, I can now calculate the joint probabilities. For example, this is the probability that the product is popular and someone buys it. Okay, and that's going to be the probability of 70% times 0.6, right? The product is popular, and given that someone buys it, so it would be 70 times 60. 70% times 60%. So it's 42%. and you can do all the calculations similarly to get these four conditional probability, joint probabilities. Okay, so now we can calculate the marginal probabilities here, right? The probability for listing to be bought and to be not bought. This will be 48% and 52%. All we need to do is to sum these two probability up, right? This is the total probability for this product to be successfully sold. So now, suppose we do all these calculations before this consumer comes in. So now we can see one consumer comes in and then goes away. So event G happened. In that case, what's the posterior belief for the product to be popular? If I ask you this question, what will be your answer? You know the total probability for the consumer to go away is 52%. When that happens, what's the probability for event P to occur? It will be exactly 28 over 52, right? You know, if G happens, there are two possibilities, either P or U. And when G happens, inside G, P counts for around 54% of possibilities. Okay, so that's why when we are asking this question, when we are asking for posterior beliefs, we are doing another conditional probability. But now we conditioning on the observation on the experiment outcome G. We are asking whether the product is really popular. So we can see one thing. After one consumer goes away, we update our belief on unpopular. We update our belief on that the product is popular from 70% to only 54%. That means we become less confident, right? Because originally I am confident, but now one guy just goes away, 就是被打脸嘛. One guy goes away, so I update my beliefs. This makes me less confident. If another consumer comes and then goes away again, I will do an update again. In this case, I will use my old posterior beliefs, 54 and 46, to be my new priors. You may enter 54 and 46 here, and then do this calculation again. You can see that my belief would become 37% only. So 70, 54, 37, I am keep updating my beliefs downwards. So if actually 5 consumers comes and then goes away continuously in a row, then my posterior belief would become just 7%. And that's a very strong evidence showing that the product is unpopular. So as another example, suppose I guess I am a good researcher. I believe I am a good researcher with probability 70%. Okay, and then I submit a paper and get a rejection. Then I update my belief to be around 50. And if I keep submitting papers and get 5 rejections in a row, I would update my belief to only 7%. And I have a strong belief that I am just the worst researchers in the world. Alright, so now we have done so, right? We have used this formula to calculate, to update my belief. In general, with the law of total probability, we can write explicitly what's the denominator, and that's exactly our base theorem. So suppose y1 up to yk, they are mutually exclusive and completely exhaustive, and x is another event. Then the posterior belief, given your observation, the probability that this product is, for example, popular, can be calculated in this formula. That depends on the total probability as the denominator and the probability for this thing to occur as the numerator. So typically, we do this when it's clear how yi's affect x, how the popularity of the product affects the sales outcome. Okay, and Bayes' theorem is doing the other direction. When we see the sales outcome, how do we infer the quality of this product, the possibility of this product? Okay, so now you realize why do we need Bayes' theorem. For example, if I am offering a warranty to consumers, consumers are using whether I am offering a warranty to infer the reliability of my product. Okay, that's something we will do in the next video. So generally, in this case, G and B, good or bad, naturally affects P and U, popular or unpopular. Sorry, this is completely wrong. Sorry, yeah. This should be P and U. Okay, popular and unpopular. They will affect goes away or purchase or buy. Yeah, but this is not the other way. Okay, so we will apply the Bayes' theorem. Yeah, and to use the outcome here to infer the quality according to this calculation, which is exactly what we got when we are using that table. Okay, so anyway, what we have here is nothing but a formula and a concept. We do not know something, and then we use our observation to update our beliefs. Okay, and this concept will be required when we do signaling games, because we're going to, based on what the principal is doing, to infer their types. Okay, now let's take a break.